just get started. So hi everyone, and welcome to another remote OWASP Norway chapter meetup. The topic for today is differential privacy, and with us we have Mirac, Vuslat, Basaran. I hope I'm pronouncing that correctly, from Google. So for the agenda for today, first Mirac will start out with an introduction to differential privacy before delving into the Google Differential Privacy Library and the specifics of its functionalities and features. Finally, we'll finish up with a short Q&A before wrapping things up. So if you have any questions, feel free to write them in the chat during the presentation, or just raise your hand after the presentation so we can have a Q&A session then as well. With that, I think I'll let Mirac get started with the presentation.
Yeah, thanks, Arvind. I hope you can all see my screen. All right. Sorry, just a second. All right. Hello, everyone. My name is Mirac, and I'm a software engineer in the anonymization team at Google. Today, I'll be talking about Google's open source differential privacy libraries. Start with an introduction into anonymization and differential privacy, because I assume there are some among you who don't know what differential privacy is or why it is useful. During the presentation, please feel free to interrupt me. You'll also have time for questions at the very end if you prefer to ask them then. To understand what anonymization is, let us consider an example. In Google Maps, you can know which hours are particularly busy for restaurants you want to go to, or learn about popular dishes in this place. Of course, the data originally used for this might be very sensitive. You want to make sure we are not inadvertently disclosing data that could be used to re-identify users or infer information about the individuals. For one, location information used for restaurant business is inherently sensitive. This is the core issue of anonymization: how to publish useful data without leaking personal information. Anonymization allows us to get valuable insights from the data, but significantly reduce the liabilities and risks associated with the data. Arguably, anonymization can be even better since it removes the collection noise. Proper data anonymization can appear deceivingly simple. However, there are a lot of subtleties and hidden stones which can result into non-obvious ways of leaking sensitive information. The naive question is, why don't we just remove identifiers? Removing identifiers might not be good enough, as well as removing PII, personal identifiable information. There are multiple well-known data breaches resulting from publishing the identified data. One classical example involves a publication of de-identified medical records in the state of Washington. Those records could be partially joined with the voting registry using birthday and postcode. This was sufficient to identify a majority of the individuals in the dataset. In another classical example, as a part of a competition in 2006 that intended to improve movie recommendation system, Netflix published movie ratings from its users. The records had the user identifiers removed, but researchers could partially join these records with IMDb dataset, which was tied to identity. Such a join made it possible to partially tie the full history of movie rankings to the user identities. This is a classical example of joining the identified datasets and re-identifying some of the users. Finally, the identified search history can also, in certain cases, reveal the identity of the user. So there's a pattern here. Even if the record is published without direct identifying information, the content of those records, together with some auxiliary information, may make re-identification possible in certain cases. Thus, we need something better than the identification in general. The second question is aggregated data. In fact, it's a very well-known technique to publish aggregated statistics within buckets of users. Usually, this involves grouping by a set of features. For example, grouping restaurant visits by location and hour. This is commonly referred as k-anonymity, since each user in the anonymized dataset is indistinguishable from at least k other users. K-anonymity provides stronger guarantees than simple de-identification, but it's not perfect either. For example, it's problematic if I'm a part of a bucket that is associated with a sensitive attribute, say a particular medical condition. It's not helpful that I am indistinguishable from k other users having the same condition. While I cannot be associated with any particular record in the database, my sensitive attribute in that example is revealed. Another example, imagine two aggregate buckets, 99 users plus me and 99 users. Publishing aggregate info about those two buckets is k-anonymous, but it's possible to identify me and my sensitive attributes by differencing those two buckets. At last, if the attacker can modify the database and create fake entries, there is no anonymity for my data if I'm a part of a crowd of 99 fake users. Those types of attacks aren't always feasible or relevant, but they cannot be excluded in general. So is there a better way to define anonymity? That's when differential privacy comes into the picture. Differential privacy is a mathematically rigorous way to define anonymity. It is a mathematical notion that captures a very simple intuition. Suppose that you have some data, which you then use to produce a nice, useful result. Now, suppose that you use the same method, except you removed one of the users. Differential privacy tells you that the results should be essentially the same. If you only look at the results, then you can't notice that someone has been added or removed. This tells you that the result did not contain information specific to this particular user. Each individual is protected. This definition makes intuitive sense. If my particular contribution doesn't affect the result, I won't mind me being present in the database. To recap, an algorithm is differentially private if its output doesn't change much when a single person is added to the database. This has a rigorous mathematical definition, which basically considers a pair of two neighboring databases, calculate output of these databases. Remember, the output here is probabilistic. It defines a threshold of the probability density functions. This threshold that defines how much the output is allowed to change is called epsilon. Here's an example to give a bit of intuition on the previous definition. Imagine that we have anonymous statistics about number of participants of an imaginary conference by country. When we add one more participant, we clearly see the effect of this in the histogram. Furthermore, we know that the newly added participant is French, and thus this statistics isn't differentially private. Once we added a bit of noise, the country of the newly added participant isn't obvious at all. In fact, we are not sure if anyone was added at all, which is the goal of differential privacy. Note that this statistics is still valuable and legit, even though it's not perfectly accurate. We can add even more noise and make this even more private at the cost of accuracy. Note that privacy comes at a cost of utility. So differential privacy has a ton of advantages. First, it's conceptually not very difficult. To obtain differential privacy in practice, you add noise to data. This noise has to be carefully calibrated. You have to balance privacy, so you want each user to be well hidden, and utility. You don't want the noise to drown out the real trends. Second, it gives strong mathematical guarantees with very nice properties. Resistance to auxiliary knowledge, so data is protected even in the presence of auxiliary data. And composition. You can use it multiple times and you still get protection. However, when we set out implementing this, we were surprised to find out that this was much more difficult than we anticipated. We realized that differential privacy is a bit like cryptography. There's a lot of things that can go wrong. Translating the research into practice also required a number of innovations. To fix some oversimplified assumptions we found, like each user contributes exactly one record to the data, often assumed to be true in scientific literature, and is rarely correct in practice. So we did two things. First, we published papers to explain how we implement differential privacy in practice. One of those papers, for example, the one on the top left, describes an implementation of an SQL engine, that allows making differentially private SQL queries. The paper describes a lot of technical nuances. Multiple contributions problem, so an individual can visit multiple restaurants or visit the same restaurant multiple times. Thresholding, so noise doesn't help if there is a new restaurant with only a few users. The other papers talk about similar practical considerations. The paper on the bottom left could be of particular practical interest. It describes the anonymization process we used for the COVID-19 mobility reports, where you can see how mobility reports, how mobility trends change during the COVID-19 pandemic. And secondly, we open sourced our differential privacy implementations, so others can reuse our work. Before I move on, are there any questions regarding anonymization or differential privacy? Yes, all right, it seems not. So as mentioned before, differential privacy has a lot of implementation subtleties, and it is hard to get right. As people say, don't roll your own crypto. This is a good advice for differential privacy implementations as well. Reusing a hardened implementation is a good idea. Our repository contains multiple tools related to differential privacy, and I'll be talking about each of them in the following sections. First of these tools are the building block libraries. Building blocks are lower-level libraries that implement noise addition primitives and differentially private aggregations. These libraries are available in three languages: C++, Java, and Go. They are suitable for research, experimental, or production use cases. However, as you can probably tell from the name building blocks or description lower level, they require some differential privacy expertise to use. So they are intended to be used to implement higher level differential privacy frameworks. And that's actually what we use them for. We will talk about these high level frameworks in a bit. Here you can see the feature coverage of our building blocks libraries across languages. We started with C++, so that is why it has more features. We aim to get feature parity across languages in the future. A common question we get when we talk about our building blocks libraries is if they are available in Python. We haven't implemented in Python ourselves yet, but OpenMind, an open source community, created a Python wrapper for our C++ building blocks library that you can use. I mentioned how building blocks are intended to be used by higher level frameworks. Privacy on Beam is one of such high level frameworks. It's an end-to-end differential privacy solution built on Apache Beam, and it is currently available in Go. It relies on the building blocks library to apply differential privacy. Beam is a distributed data processing framework for working on huge amounts of data. It works very similarly to the MapReduce model. So using privacy on Beam, we could do differentially private computations on large amounts of data. In addition to being able to work with large amounts of data, privacy on Beam is also out of the box. This means it takes care of all the steps necessary for differential privacy. So no differential privacy expertise is needed. Because of this, and because even experts can sometimes make mistakes, we recommend using Privacy on Beam instead of the building blocks library. We also have a MySQL code lab for Privacy on Beam. If you wish to have a quick introduction to doing differentially private computations on Privacy on Beam, we suggest going through that code lab. You can find the code lab on our repository or through a quick Google search. We also host some periodic events where we walk the participants through this code lab. So you can also watch out for these. Similar to Privacy on Beam, we have an end-to-end SQL differential privacy solution built on ZetaSQL. For those who don't know, ZetaSQL is a SQL language by Google. The differential privacy part of ZetaSQL also relies on the building blocks library. So this is how ZetaSQL DP looks in action. Above is the raw, non-differentially private version, and below is the version with anonymization. As you can see, you only need to make a small change in the query. So you add select with anonymization options, and instead of doing a count, you do an unknown count. So making this small change, and you can make your queries differentially private. We also have a code lab that walks you through how to use ZetaSQL DP in our repository, if you'd like to check it out. We also have an extension for doing differential privacy in Postgres. However, this is less end-to-end than ZetaSQL, meaning that you have to take care of some differential privacy-related stuff yourselves, and it is less stable. So we recommend using ZetaSQL instead. We have a tool, DP Accounting, that helps you get the most out of your privacy budget if you have many DP aggregations. It does this by computing a more accurate estimate of the total privacy budget used across many DP aggregations. So this might be of interest to you if you want to compute many aggregations in a differentially private way. DP Accounting is only available in Python for now. We also have a testing framework to automatically detect bugs leading to DP violations. We use this to test our own implementations. And you can also use it to test your own differential privacy implementations. So that was an overview of the tools in our repository. Now I would like to talk to you about a bit about our future plans. We have two main plans. First, we would like to achieve feature parity across languages and tools. So you remember that feature matrix I showed you earlier. So you would like to have feature parity there. And next, we plan to develop new functionalities and tools. And this includes developing existing tools in different languages as well. I will briefly talk about what we aim to accomplish in the short term as well. One of our current projects involves quantiles. We do have an existing quantiles implementation in the C++ building blocks library. However, it has some drawbacks. It is not scalable, and it doesn't allow multiple queries without spending extra privacy budget. So if you want to, if you wanted to compute a 10% and 20% and 50% quantile, you have to use extra privacy budget. So we have come up with a new algorithm that is both scalable and it allows multiple queries without spending extra privacy budget. So you can make arbitrarily many quantile queries with the same budget. We will be implementing this in all three languages or the building blocks library. So that is Java, C++, and Go, and privacy on B soon. In fact, between the time I prepared these slides and now, we have implemented an open source quantiles in Java. We also plan to do a refactoring of our approximate bounds algorithm for improved code health in C++. Go and Java will follow the same design when the algorithm is implemented in those languages. Speaking of implementing existing tools in different languages, we aim to publish a C++ version of the DP accounting tool, which is available currently in Python. Due to it being implemented in C++, we also expect it to be faster. I also want to talk about some of our long-term plans. I mentioned how OpenMind created a Python wrapper for our building blocks library. We will be collaborating with them on implementing privacy on Beam in Python. In fact, we aim to have a pipeline DP design and implementation that could be used to implement differential privacy libraries for other data processing frameworks, such as Apache Spark. We are also exploring implementing a Java version of privacy on Beam. I use the word explore intentionally here because we are not yet sure if we can actually go through with this due to some technical difficulties with Java. We actually started publishing our quarterly roadmap with the external community. The short-term plans I mentioned a couple of slides back were actually taken from that newsletter. If you'd like to subscribe to that newsletter, you could join the group here. In this group, DP open source users, we will publish our newsletter and send out announcements. You can also use it as a public forum and ask questions about our libraries and tools. So I recommend subscribing to it. If you wish to contact us privately, say if you want to ask questions or provide feedback privately, you can send an email to dpopensource@google.com. We are also curious about how people use our libraries and why. As you can imagine, it really motivates us to put more effort into open sourcing when we see people putting our work to good use. So we would appreciate if you could let us know if and how you use our libraries. Of course, this being an open source project, we are very much looking forward to contributions as well. If you wish to contribute, you could contact us first or directly take on the existing issues on GitHub. For example, you could be involved in implementing privacy on Beam in Python or Java. We would really appreciate that. Or you could take on more researchy, exploratory tasks if that's something you're interested in. Thank you for your attention, because I know that was a lot to digest. I'm happy to answer questions if you have any. So I see one question. How does this work compare to diffpare in TensorFlow? I believe you are referring to TensorFlow privacy. So that work has been done by, I would say, partners. It also provides differential privacy. The difference here is, so when you are developing an ML model, you can either anonymize the training process by adding, I believe that's how it works, by adding some differential privacy noise to the nodes in your model, in your training, or you could anonymize the data set, the input data set you use for training. So both would, in the end, make the output differentially private and anonymized. Yeah, thanks, Ria.
Yeah, I was actually going to ask that question myself if no one else did. Do you have any particularly interesting use cases of your libraries that you can share with us?
So this all the way back. Yeah, so this Google Maps graphs the busy times of restaurants or the popular dishes on Google Maps when you look at a restaurant. Those use these libraries and implementations exactly. Another example would be the community mobility reports we mentioned. That uses the SQL engine, the Differential private SQL engine, that it uses location data and to produce those mobility trends. People have been spending more time at home in their residence. People have been spending less time on retail or restaurants, those stuff. So I think those are very exciting use cases. Yeah, definitely. Traffic one is very useful. A question: could you talk more about how you maintain the privacy budget in ZSQL, especially in the face of a database that is being updated? Privacy budget topic is a tough one. Usually, so this also hasn't been, I would say, perfectly addressed in scientific literature either. So with privacy budget, you usually want to have some definitions. For example, what are you actually protecting in the database? Are you protecting only like users, or maybe you're protecting user country, so a user's contribution to a particular country, or maybe in the case of databases that are being updated, maybe you are protecting users over a time period. Maybe you're saying, my privacy unit is, and my privacy budget that I allow for that privacy unit is user across a month. So with ZSQL or in other tools, you have to decide on the budget yourself, right? You specify the budget use. I'll just quickly show you that slide. So here, as you can see, when you make this query, you use the epsilon of 1, delta of 1 to the 10 to the power minus 5. And that's the privacy budget you use for this particular query. So that means if you use multiple queries, if you make multiple queries, you have to compose them. So you can do a very basic composition by just adding them, or you can do a more sophisticated composition by using that DP accounting tool, this one that I showed you. And you can get a more accurate estimate of the total privacy budget used. But in the end, as the user of the tool, you decide. Does that answer your question?
Yeah, partly. So of course you can compose as you're saying. But so the reason I ask about this when the underlying data is updating, because it's of course really difficult, and I haven't really been paying attention to the field the past 2 years. So curious if there's been any new research that helps you with maintaining the budget when you update the data rather than the composition or algorithm in itself.
I'm not aware of any. So I think there has been some progress on the composition research.
Okay.
yeah, but database being updated is more tricky.
Yep. Thank you.
I actually have another question. You might not be able to answer it or be able to comment on it for whatever reason, but I seem to remember maybe a few years back, in the context of browser fingerprinting, there was some research as to if and how one could apply privacy budgets for that reason. So to sort of, I think the main idea was to basically to limit the information leakage to any one source via browser APIs, for instance. I don't know if you are able to comment on any such use cases, for instance, or maybe you've heard of other projects using it for those reasons, browser extensions, perhaps.
So I'm aware of one thing. So the differential privacy I talk about here is the central DP, central model. So there's also the local model where you add noise in the source. For example, in the browser, before sending data to whoever owns the browser, you add noise before sending them. So it's even differentially private, like at the source level. So actually, Google published a paper. I don't remember the exact name, but the model is called Rappor, R-A-P-P-O-R, Rappor, about using this local differential privacy to get telemetry type of information from browsers, like diagnostics type of things. Because the thing is, with local DP, because you add noise in the source, you have to add a lot more noise. So you need a lot of data, and if it doesn't really work for a lot of use cases. But I'm not aware of any other browser-related privacy things, privacy budgets.
I see. I'll be sure to check that paper out for sure. While waiting to see if there are any more questions, maybe I could just ask another one, though it's very general. I mean, I know you guys in Apple, you collaborated on the exposure notification APIs, right? For to be able to do exposure notifications in the context of COVID-19 via smartphones, and I could see interesting use cases, whether in that concrete case or other similar cases for the future. I don't know if that's something you've explored already, maybe in research for collecting health or contact data in general, maybe.
So I can't comment on particular use cases. So that notification exposure technology, I believe there are white papers and stuff about that, like the technology used there. It's quite safe. Doesn't leak any information. It doesn't send any information and stuff. But as you mentioned, health data, I think so. I'm personally quite enthusiastic about differential privacy and its uses, and I think it's not only important because it provides privacy. I think it also enables new use cases. So it allows you to do more things with data that you can't normally do due to privacy concerns. And I think health data and location data are of particular interest here because they're both very sensitive. We also see this happening in as you said, in literature and in other companies. I believe Google also, if I remember correctly, Google also provides some differential private data sets to researchers. Yeah, definitely very, very important use cases. Another important use case, this is not from Google, but the 2020 census, US census, is using differential privacy. And I think that was quite an important step for the differential privacy.
It's very interesting. Right. So there hasn't been any other questions than where the recording will be put later. So with that, maybe we should call it a night or an evening. Unless there's anything more you would like to say on the tail end of the presentation.
Yeah, just that I'll again show this slide really quickly. Yeah, if you have any questions or comments in the future, please reach out to us. We're always looking forward to hearing from you. And thanks for listening.
Great. Thank you so much, Mirac, for making an appearance and giving a great presentation. And thanks to all the other guys for showing up, and I hope it's been interesting. So keep an eye on our meetup group, as we'll be announcing more virtual meetups shortly, and enjoy the rest of you guys' evenings.
Thank you very much. Bye, everyone. Have a nice evening.